Thank you for the introduction. So, that should work. Good. Let me start with a very simple question. When a new event occurs, how do we characterize it? In practice, we'd like to know two things: where it happened and how strong it was. Now, if we look at this global map, we see a striking diversity. Events span over all magnitudes in well-instrumented regions as well as in sparse ones. So this uneven coverage raises a fundamental question. How can we produce reliable estimates when the data is so irregular, both in quantity and in quality? Here is a concrete example using full-wave modeling. For this CTBTO relevant case, regional seismic data, shown in red, suggests a yield close to 1 kiloton. Infrasound data, in blue, gives a much smaller value, and empirical laws let you to other values. So what's the problem? First, different technologies do not agree. Second, even within the same technology, different methods can diverge. And more importantly, there is no real sense of collective inference. Stations are treated in isolation. This is where graphs come in. So instead of analyzing stations one by one, we can represent the whole network as a graph. Vertices correspond to stations. Edges encode relations, such as travel time, correlation, or distance. Each vertex also carries its own features, its own information, waveform characteristics, spectral attributes that provide the local information. So the real challenge is to design a method that not only predicts the characteristics of new events, but also remains flexible enough to adapt to such heterogeneity. Here is a concrete example from seismology, a French seismic network. The data shows the seismicity since 1995, and as the animation runs through the years, we clearly see strong variability. Events occur with very different magnitudes in different regions and at different times. Sometimes the network provides dense coverage, while in other cases, only a handful of stations are nearby. So the real challenge here is to design a method that not only predicts the characteristics of new events, but also is flexible enough, you see, to adapt to this heterogeneity. So this brings us to the concept of dynamic graph neural networks. So the key idea is that the graph cannot be predefined. Instead, the model must learn the graph, deciding which stations to connect and how strongly. This is achieved through graph convolution layers that capture relationships between stations directly from the waveforms. But beyond that, there are other advantages in using graph neural networks. Stations can evolve, models can be transferred across technologies or regions, and they remain stable when the data is noisy or incomplete. So you have understood that I'm going to talk about graph neural networks. So you see, the idea is very simple. Instead of treating stations as isolated sensors, we want them to collaborate. What begins as a set of independent nodes becomes a connected network where information can flow and be shared. OK, good, but how does it work in practice? At the heart of GNNs lies message passing. Each station collects information from its neighbors, aggregates it, and updates its own features. And this is repeated layer after layer. But here comes the real question. Who are the neighbors? So indeed, we could fix them, for example, based on distance. But the real strength of graph neural networks is that neighborhoods can be adapted dynamically depending on the feature themselves that depend on the layers. So now, in practice, we generate edges in two complementary ways, by geographic proximity and by feature similarity. That means stations can be linked because they are close in space or because they capture similar waveform patterns. So at each layer, features are updated by mixing station's own information with what comes from its neighbors. And importantly, this update also depends on the differences between the features, so that each layer uncovers new aspects of the seismic field. Stacking several blocks, several spatial-temporal graph convolution layers, we obtain a multi-scale embedding. Shallow layers capture the broader patterns, while the deeper layers focus on higher-order correlations. So now let's have a look at the overview, at the architecture. So we have 4 steps. The first step, extract information from the raw waveforms to produce the features. Then you have these graph convolution layers. Then you have what we call an aggregation step that condenses the information. And finally, you have the prediction step. Now we have another architecture which is much simpler, which is our baseline. We call it edgeless graph neural network. So you see it, the gray line. You have a fully connected neural network, very simple, without any graph structure. Let's move to the numerical results. We evaluate our method, our approach, on 2 contrasting data sets. A French seismic network, which is relatively sparse in blue, and a Southern Californian seismic network, which is much denser. Diversity is important because it allows us not only to test accuracy, but also to see how the model can generalize across very different recording conditions. But so here, what you have is the distribution of station to even distances. So it highlights the contrast. In red, the Californian network, and in blue, the French network. To make the comparison fair, we use subset of only 1,000 events, which is very small for machine learning application. And we restrict the analysis to local magnitudes larger than 2.5. Another difference is that the SCSN provides 3-component recordings, while FSN, the French one, is mostly vertical. Finally, waveforms are pre-processed before being passed to the graph neural network. But before looking at results, let me quickly clarify the error matrix we use. We distinguish 2 sources of variability. One comes from the data, using k-fold cross-validation, okay? 90% for the training and 10% for the validation. And the other comes from the randomness of training, explored with multiple seeds during optimization process. Combining these with several GNN variants and 2 data sets means we end up training more than 1,000 models. For each model, we compute the root mean square misfit with respect to the catalog values. And we also track the eigenvalues learned through variance decomposition. So here you have the impact of spatial-temporal graph convolution. The learned uncertainty is very small, 0.02, much lower than what bird teams usually report. So compared to the edgeless baseline, STGC, the graph convolutions, improve the accuracy and reduces variance for both the French and the Californian networks. So on the left, you have the edgeless GNN, so without any graph structure, and on the right, you have the dynamic one. Now, if we decompose the variance, sorry, we see that most of it comes from the data, and in particular, from the poorly sampled magnitude ranges, where variability is higher. Yet, even under these conditions, the error remains well below the level expected by analysts in daily practice. So overall, dynamic graph neural networks make predictions that are more stable, less biased, and more reliable. Now, we evaluate the robustness by removing spatial and temporal content from the waveforms. One, we use the full spectrum between 1 and 8 Hertz. Second, we restrict it to a narrow band, which removes most of the spectral richness. And then we add random time shifts. You have the result here. So edgeless on the left and dynamic graph neural network on the right. So we see that without STGC, the model collapses. With STGC, the model adapts and still delivers accurate predictions, even under strong corruption of inputs. If we add multiscale embedding, the robustness is reinforced, and the model avoids the classical error drift that comes with deeper architectures. So the key takeaway is very simple. STGC ensures robustness, and multiscale embedding stabilizes learning. Let's now have a look at the interpretability of graphs for 4 new events that were not in the training dataset. You see how the edges evolve across the graph convolution layers. Colors highlight which stations the model considers most influential. Often, these are the closest stations, closest sensors, but sometimes distant ones carry unique information the closed station, the closed network cannot. So definitely the model is not a black box. It reveals which stations matter and how relationships change to improve accuracy. By the 4th graph convolution layers, compact clusters emerge around the epicenter, even though the epicenter was not given as input. So, okay, so far we've seen that STGC organize stations as clusters, automatically select the most influential ones, but now, instead of reducing this to a few parameters, as graph neural networks usually do in their final step, we'd like to project this information into a latent space of a few hundred dimensions. In parallel, bulletins could also be encoded with a text model and projected onto the same space. A shared latent space is what makes multimodal alignment possible. Let me show you now the architecture. So we implement this using dual encoder architectures, pre-trained dynamic graph neural network for waveforms, and a pre-trained text model for the bulletins. Both are mapped into the same latent space so that bulletins and time series can be aligned directly. Training combine contrastive loss for alignment, a stability term, and a dedicated loss from a shallow neural network, which is the step number 4, which predicts the magnitude, depth, and location. Let me just give you one important result. Here, with our hundreds of dynamic graph neural networks trained on the French dataset, under very different hyperparameters, we observe a systematic bias of 0.3 against the external estimates, external magnitude estimate. Now, once we add bulletin informations, stripped off analyst-based predictions for the magnitude, the bias shrinks to 0.1. So to our knowledge, this is the first time bulletins, so structural knowledge from technical bulletins, has been integrated in the state-of-the-art machine learning framework. So it marks an early but promising step toward more consistent estimates across agencies. So to wrap up, now graph neural networks move us from isolated signals to collective inference. With dynamic learning, we achieve near-expert accuracy, robustness, and analyst-oriented interpretability. With LLMs, it unlocks tasks that we could hardly imagine 1 year ago. Thank you very much for attention.
Many thanks for this presentation. Would anybody like to ask a question? Yes, please.
So thank you very much for your talk. Could you elaborate a little bit on how the model is accounting for side effects and attenuation in order to extract similar, I mean, it is very simple to see how you can extract similar things when the stations are closer between each other, but when they separate, attenuation effects start playing a key role. So how the model is accounting for these attenuation effects?
If I understand correctly the question, your question is about the latent space. Indeed. We use a technical report or technical bulletin to obtain a vector in a latent space of high dimension, it's 255, and we can also project the output of the first third parts of the dynamic graph neural network to have a vector. And then maybe your question is about the contrastive alignment, the contrastive loss alignment. So this is quite well known in the machine learning community. So you can have information from text reports, you can have information from physical sensors, and then you can combine them into the same space and align them. So it is called contrastive alignment.
Any more questions? I would have one. So this network then is going to, as it acquires more and more events over time, such a network, such a graph neural network, would it continue to adapt itself?
Yep.
Okay. Mm-hmm. And what would you expect then would happen when you have an outlier event, say a nuclear explosion or something like that? That does not fit into the standard characteristics of what the network has adapted.
A result for the magnitude, but we also have the depth and the location. So the output of the dynamic graph neural network is first, of course, predictions at a very low CPU cost. It's maybe less than 1 second. You only need to have the waveforms. So you feed the dynamic graph neural network, and then it predicts. First, so magnitude and so on. Second, you have interpretability. So it gives you the stations that matter, so the most important stations, which means that you select automatically the stations in order to improve accuracy, to provide a magnitude estimate. So you can give these stations to analysts to compare if they are coherent with the choices that are done by analysts to predict, to obtain a magnitude. And you can also use the output in combination with bulletins without the magnitude estimate. That's very important, so you strip off this information. And then, by alignment, you have a better magnitude estimate, because you decrease the weight given to this supervised component in order to have a better alignment between two different sources of information.
Okay, and when an event is analyzed by the network, it's also possible then to see what kind of features it determined to because that gives insight then in whether there's something there in the physics that is interesting to follow up for analysts, for example,
Yes.
right? Okay. Thank you. There's no other questions, also not from the internet, no? So, well, at this point, this concludes our oral session. We would like to thank you for participating and thank the authors for their very interesting work and presentations. And we look forward to seeing you at the next SNT. Thank you.
Thank you.